And here we are. Okay, so we're looking at convex spherical mirrors. Like we've pointed out, concaves are shaped like this. Convex, so your objects here. Convex mirrors are going to be shaped in the opposite direction, so they're kind of coming at you. If you take a look at your spoon, where'd my spoons go? If you take a look at your spoon, your convex side is going to be the back side of the spoon. Okay, so not the like cereal side, but the back side of the spoon. That's convex. It's bubbling out. And whenever we look at a convex mirror, like our spoon or whatever you've got, what you're actually going to see is the following setup here. You're immediately going to notice that no matter if you're really close or really far away from that spoon or convex mirror, you're always going to appear right side up, which means that you're always going to be virtual image. So when we're looking at this concave and then convex mirrors, we're always going to see just a virtual image. It'll just be upright here. And the way we actually generate this image on this convex mirror is as follows. We see like the final solution up here and what we're going to see. But how do we do it if we're just kind of like working at our papers? Okay, so here's a convex mirror. Here's a principal axis running through it. And then here is some object. Well, when we draw our ray diagrams, it's important for us to remember that there is a focal point on this mirror, but the focal point's actually on the inside of the mirror here. The focal point's back here, which means the center of curvature, as I measure it, boink, boink, is about here. When I go ahead and I trace out my rays, what's going to happen is a ray of light is going to hit this arrow, and then it's going to bounce. And then when it hits the mirror here, it's going to reflect off of this mirror so that the angle of incidence equals the angle of reflection. And when that happens, what actually occurs is that this ray is going to bounce like this. So this is the actual ray of light. It's bouncing away. And if you take a look at these rays of light all over the place, all of the rays here, as they strike this, all of the rays are going to bounce away. So all of the rays on this side are actually going to diverge. We're going to get rays that like bounce like this, and if they bounce off the center, they're going to bounce like that. Like all of the rays over here are diverging. Okay? So we're actually not going to be able to create an image on this side, but your mind still sees something. And here's how it sees that virtual image. Once this original beam of light hit off the mirror and went up like this, your eye has to think to itself, because your eye is over here somewhere, your eye is thinking to itself, where did that ray of light come from? And because your eye only thinks light moves in a straight line, your eye moves that ray of light backwards. And it says, look, that ray of light clearly came through the focal point. So that goes right through the focal point right there. Your eyes will also see the following. If you took a ray of light and you went from your arrow and you passed it through the center of curvature, the angle of incidence here and the angle of reflection for this orange line are actually going to be normal or perpendicular to this surface. You're going to hit it such a perfect way that the light literally hits in and bounces straight back out. And that maps back through the center of curvature. If you do that, notice on this side, these light rays have now intersected, which means that your eye thinks that the image is right here. Really, there's no light over here. This is all dark. Okay, there's not a single speck of light here, but your eye thinks there is. So that's what's going on with a convex spherical mirror. All of the light is hitting it. It's reflecting out and diverging, and we can see up here like all of these light rays, like I said, these are going up, these ones are going down, they're all diverging, but when we move them back, we see that there is an intersection point, and that intersection point creates us an image. And as we see here, this image is upright, which means it's going to be virtual. It didn't flip. This arrow's up, this arrow's up. And it has actually become smaller. This will always be the case. Okay? In a convex spherical mirror, the image will always be smaller than the object. And you've seen a case like this every single time you've been in your car. Whenever you look at your right passenger side side mirror, there's a little bit of text on the bottom that says objects in mirror are closer than they appear. Well, the reason being is that is actually a convex mirror. It's convex to give you a wider angle to look at so you can see into opposing lanes or lanes to the side of you. But because of that, all of the images that you see in the mirror have become smaller. So the objects are actually closer to you. They're actually larger than what they appear in that mirror. So that's why you see a smaller image like that is still upright on these convex mirrors. And that's how we draw them with our ray diagrams. What we're going to take a look at momentarily is spherical aberration. And we'll also take a look at in that video of just how these images are always staying upright using our ray diagram kind of sheets. But until next time, adios and take it easy.